Okay, section 1.9, and this will be the last method we discussed for differential equations of order 1. All right, of course, there's a few more methods like Riccati's equation, Clairaut's, and Lagrange equations. However, well, in a 3-unit course, we definitely don't have time to cover every single method. I wish I had time, right? But it's simply not feasible. Anyway, so section 1.9 on exact equations. Well, what we're going to do here? So we're going to do a little bit more on partial derivatives. All right. We're going to do a bit more on partial derivatives because we need them for just in order to solve these exact equations. Well, actually, I gave you for those of you who haven't taken Cal 3, I gave you like a crash course on partial derivatives when it came to solutions, existence and uniqueness of solutions to differential equations, to IVPs, right? However, for this topic, we need not just the first derivative, we need a little bit more than just that. Okay, so they're asking us here to find all second order partial derivatives, not just the first derivative, but the second derivative. Well, so number one, here's the thing. Just to give you an idea of how multivariable functions work, I mean, for those of you who haven't taken Calculus 3, okay, so we have a function of two variables, some f of x, y, all right? Well, it turns out, as we did back in a couple sections ago, we can take the partial with respect x or the partial derivative with respect y. All right? Well, once we are done with with the first order partial derivatives, we can take the second partial derivative. However, there's a total of 4 second order partial derivatives. Number one, okay, whatever we already differentiated with respect x, we can differentiate it a second time with respect x. All right? That is twice with respect x. Or whatever we differentiated with respect x, then we can differentiate it with respect y. All right? And then, well, what's next now? What if we go on the second branch? What if we differentiate first with respect y? Okay, we can differentiate again twice with respect y, or first with respect y and then with respect x. This is just so you get an idea of the work we're going to do about this function. Now, think about it. Think about a function of 3 variables, all right? Think about a function of 4 variables, how big this tree diagram would look like. And what if we wanted to find like all the 50 derivatives of a 7-variable function? Can you think about it? All right, well, that's actually what you're going to do in engineering problems. I mean, not by hand. You're going to program all this, how many variables you have, how many processes are you going to do. So it's all automatic, right? So you're going to do that later, okay? So this is like to give you an idea of how that works. Okay, well, number one, let's find the partial with respect x. Okay, the partial of x cubed, which is 3x squared. Okay, so 3x squared times a third, that's just x squared times y cubed. Again, the y cubed remains there because it is a multiple constant. If it were an additive constant, well, it vanishes to 0. All right? Okay, what about the partial with respect y? Okay, same. 3 times 1/3 is 1. X cubed is just a multiple constant, and then the derivative of y cubed is y squared. All right? So far, check on these two. Let's talk about these 4. Okay, so f double x, f twice with respect x. So that means, check, what we already differentiated with respect x, differentiated again with respect x. That is, the derivative of x squared is that 2x y cubed, okay? And then I'd like to do f twice with respect y. We're gonna talk about the other 2 in a second. That is, whatever we differentiated with respect y already, do it a second time with respect y. All right? Okay, what about, okay, first with respect x and then with respect y. So here, what we already differentiated with respect x, differentiated with respect y. Here, the derivative of y cubed is 3y squared. That is 3y squared, but because of x squared being a multiple constant, well, it remains there. Okay? Now, what about f with respect y, then with respect x? Okay, what we differentiated first with respect y, differentiated again now with respect x. So that is differentiate x cubed with respect x. So that is 3x squared y squared. What do you notice about these results? Do you notice anything interesting about these results? Dwayne? They're the same, right? These two are the same, all right? So, same. Well, there's actually a name for this. These are called the mixed partial derivatives. And no matter what function do you have, that's always true. That always gets satisfied. It's always true. If you take the second order mixed partial derivatives, there it's always going to be the same. Well, so let's put it in more formal terms. It's actually called Clairaut's theorem for mixed partial derivatives. So it tells us that if f is a function of x and y such that the mixed partials are defined on some open disk R, then for every point in the region R, this is always true. That is, the partial derivatives, the mixed partial derivatives, second order actually, they are the same. Well, we can extend this idea for third order partial derivatives, for order partial derivatives. Well, that's something we're going to get to see in Calc 3 for those of you who are taking it, right? Well, now also in Calc 3 we talk about the total differential. What's the total differential? Well, number one, let's find the differential of some function f of x, like f of x equals to 2x. Well, let me call x squared. Y equals x squared. Well, to find the differential, all we do is simply say dy equals to the derivative of the function x squared, which is 2x, and multiply by dx. So that's the first time you see the quotient dy dx, which denotes a derivative as a quotient between two quantities here, right? And well, so this is the differential of the y variable related to the x variable. However, for functions of two or more variables, we're going to do partial derivatives to get these differentials. However, each partial derivative, the one with respect x and the one with respect y, we need to multiply by the dx and dy because we have two variables changing, two independent variables changing, dy and dx. So that's the Jacobian notation or the subscript notation. All right. Well, let's have a look at this. Let's see this in action with the next exercise. Okay, so they're asking us to find the total differential of the function f of xy equals to 1/3 x cubed y cubed. And I'm just using the same function from the preliminary example just to move on quickly. Okay, so they're asking us to find. Okay, instead of the z, this can actually be simply df equals to the partial of f with respect x dx plus the partial of y with respect y. Not the partial of x, the partial of f with respect x. And then the partial of f with respect y, dy. We don't need to calculate this anymore because we already calculated in the previous page, right? So, the derivative with respect x from the previous page, with respect x, x squared y cubed, and then with respect y, x cubed y squared. All right? So, let's go ahead and simply substitute the df equals to x squared y cubed dx plus x cubed y squared dy. So in this case, We call it the total differential because we're not just taking the differential with respect to x, we're also including the differential with respect to y. That's why we call it the total differential, all right? Considering all variables. All right. Well, where are we heading with this? Well, these are just the tools, these are just the tools we need in order to see what's coming up right here, which is in this case the solution to an exact equation. Okay, so let's see about it. All right, so let's have a look at what exact equations look like. So a differential expression m of which is a function of x and y, dx plus another function n of x and y as well, dy, it's called an exact differential in some region R of the xy plane if it corresponds to the differential of some function f, right? So that's what we did in the previous part, essentially. Okay, so actually, a first-order differential equation of the form m dx plus n dy equals to 0 is said to be an exact equation if the expression on the left-hand side of this equation corresponds to an exact differential. All right? So, guys, just so you don't get confused, actually, this looks a lot like, remember the homogeneous equations? Actually, it's the exact same format. However, many of those homogeneous equations can also be solved with the method we're going to discuss here. All right? Now, let's get into the condition for an equation to be exact. All right? Okay, so definition. So let m and n be continuous and have continuous first partial derivatives in a rectangular region R defined by some rectangular bounded between a and b and c and d. Then a necessary and sufficient condition for this expression to be an exact differential is that the partial of n with respect to y equals to the partial of n with respect to x. For those of you who already took Calc 3, we got to see something like this in vector calculus in chapter 17. Remember when we were doing, what was that, conservative vector fields? So it's going to be the exact same process, but to solve a differential equation. Well, actually, I would like to prove this result because, I mean, I could give you the method in a couple minutes and solve 2 or 3 problems in another 5 minutes, but I'd like to show you the connection between this condition and what we do in Calculus 3, which is a pretty cool connection. Okay, so what's the proof right here? So consider consider that m dx plus n dy equals to the partial of f with, okay, let me do partial f with respect x dx plus partial of f with respect y dy. So that's okay. That's considering that that expression m dx plus n dy, it's a total differential, right? Because of this, we're trying to connect that. Okay. So from here, it follows that okay, I'm going to equate coefficient. The coefficients of dx where m equals to the partial of f with respect x. All right. Plus. And also, that's okay. Let me call that number 1, and n equals to partial of f with respect y. So, that is, let me call this 1, and let me call this 2. Okay? So, this is what we're going to do here. So, I'm going to differentiate y, number 1. Okay, let me do that on the side. Differentiate 1 with respect to the variable y. All right? So what is that going to be? Okay, what's that going to be? So number 1, let me use different colors for this. So the partial with respect to y of m equals the partial with respect to y of partial of f with respect x, right? And secondly, we're going to, okay, what is that going to be? Okay, let me just clean this up. So that's going to be partial of m with respect y equals twice partial of f, first with respect x, and secondly with respect y. All right? So that's what we get by differentiating both sides of number 1 with respect to y. We're going to do something similar here. Okay? Do something similar. Differentiate 2 with respect to the variable x. Okay? So this means we're going to differentiate with respect x and with the variable n, and that equals the partial derivative with respect x of partial of f with respect y. All right? So this means partial of n with respect x equals to partial double the second derivative of f first with respect y and then with respect x. And here's where we put things together. All right? Well, so with this, so from mixed partials theorem, we have that partial, the second partial first with respect to y and then with respect x, it has to be equal to the second partial of f first with respect x and secondly with respect y. All right? Well, this means, what does that mean? Partial of m with respect x, okay, I mean with respect y, equals to partial of n with respect x. And with this we prove that that condition. Actually, this is a proof I don't do in the Calc 3 class, but I'm doing it here in the differential equations. And that's just to show that this is still true. All right, we're going to do a few more proofs related to this. Okay, we still need another tool from Calculus 3 before getting to solve these exact equations. And guys, this may seem like a lot of work, but trust me, the method of solution to these equations is just going to go very, very quickly. All right? So there's more derivations and theory and explanations than actually work. Okay, so we need to talk about partial integration. Now that you guys know about evaluating partial derivatives, well, we can evaluate a partial integral. All right? Well, but here's the thing. What happens if we evaluate the integral of 2x dx? What do we get? X squared plus some constant of integration, right? So, but that's for the one variable case. However, when we are evaluating the integral of a function of 2 or more variables, if we partially integrate it with respect x, okay, what are we doing? We're holding the other variable, in this case y, or as many as you have, we hold them constant. So that means the constant of integration, that the one that looks like this from Calc 1, it's going to be a constant, which is a function that depends on the other variable that we held constant, all right? If we integrate with respect y, we're holding x as a constant. So this constant of integration will be a function of x, or maybe just a number depending on the conditions, okay? So let's see. Let's have a look at a couple of examples. So number 1, let's integrate 2xy with respect x. That means we need to hold the variable y as a constant, all right? Well, so focus on integrating 2x. Again, the integral of 2x isn't that x squared times the multiple constant y plus c. However, this is not just a plain vanilla c. This is a c which is a function that depends on the variable or variables that we held constant upon this process. In this case, since this is just 2 variables, so this is going to be a function of y. All right? And that's final answer. Okay, for letter B, the integral of e to the xy dz. Okay, notice in this case we not only have 2 variables, we have 3 variables, okay? And well, what do we do in this case Okay, so let me show you. Number one, when we integrate something like e to the 2x dx, isn't that itself e to the 2x plus c times 1/2, right? Or in general, when you have something as simple as this, e to the ax, that's 1 over a, e to the ax, plus some constant of integration, all right? So we're going to use the same principle here to evaluate this integral. Well, so in this case, we are integrating with respect the variable z, right? That is, focus on integrating with respect to z. Everything else, x and y, is just going to be a multiple constant, right? Okay, so that is the integral, okay? Well, no, that's simply itself. The integral of an exponential is itself e to the x, y, z times 1 over a. But a in this case is whatever is multiplying the variable we are integrating with respect to, which in this case is a variable z. The coefficients are x, y, plus some constant of integration. However, this constant of integration is not just the letter c. It's a function of the variable or variables, in this case variables, that we held constant, a function of x and y. All right? So we need this. Okay, we still need a little bit of partial integration to get to solve these equations. All right, finally, the method of solution to exact equation, to exact differential equation. Okay, so here are the steps. Number one, verify that the equation is exact by checking this condition. Like in Calc 3, we will use this condition to check whether a vector field is conservative. Here, we're going to use the same condition to determine whether the differential equation is exact. I already proved this result, right? So at this point, we believe this, okay? Number two, once we know that the equation is exact, evaluate the partial integrals, m with respect to x and n with respect to y. All right? Just like retrieving a potential function, which is actually that potential function will be the solution to the differential equation. Will be the solution whose total differential equals the equation we got. All right? So very similar. Now here's the thing. When we find these two integrals, do not combine any duplicates of terms. Actually, we will consolidate result. I'll show you what that means, right? And finally, that function we obtained, let it be equal to some constant c. Okay, let's see. Let's have a look at one example. All right. We have solved each equation, okay? Each exact equation, not partial equation. Okay, so let's label number one. So 2xy dx, 2xy equals our m, and x squared minus 1 dy, where the x squared minus 1 equals to n, and that equals to 0. So number one, let's check whether this is an exact equation. So number one, find the partial of m with respect y, and that equals the derivative of 2xy. The derivative of y is 1 times 2x, which equals 2x. All right? And what else? The partial of n with respect x, okay, go to n, differentiated with respect x. What do we get? 2x. What does that mean? These two, they match. All right? This means, therefore, the D is exact. All right? And we're ready to solve it. How? By evaluating the partial integrals. Okay, so the integral of m with respect x equals the integral of 2x y dx. Well, actually, we already did this integral, right? Is that x squared y plus c, okay, x squared y plus c of the c of y, if you will, all right? That's one. Number two, let's evaluate the integral of n with respect to y, okay? So that's the integral of x squared minus 1 dy. Be careful when evaluating this integral. Well, the integral of x squared with respect to y, it's not x cubed over 3. We are integrating with respect to y, all right? So the integral of a constant and dy will be the constant x squared times the variable y, minus the integral of 1 dy, which is minus y, plus some function of x. Okay? Alright guys, well, here is where we form our solution. Okay? So number one, I'm going to highlight all the different terms we see. For instance, we have let me make this bigger. Okay. We have an x squared y. Do you see another x squared y? There's one in the second integration, right? Okay. Do you see a different term other than x squared y? If so, which one is it? The negative y. Okay, let me highlight it along with the sign. And well, this is how we are going to form a solution. Grab one sample of each. Again, do not combine duplicates. Do not combine duplicates, okay? So this is f of x y equals to x squared y minus y, okay? And we're going to set x squared y minus y equals to c. And that is the solution to the differential equation. That's our solution. All right. Okay, well, let's have a look at another example. All right, the next one. Yeah, I like the next one. Okay. So, letter B, x plus sine y dx plus x cosine y minus 2y dy equal to 0. So number one, let's identify our m and our n. Okay? So number one, let's perform the test to determine whether this equation corresponds on the left-hand side to a total differential or to an exact form. Okay? So that is partial of m with respect y, which is, okay, the derivative of x with respect to y, x is a constant, that goes to 0. The derivative of sine y with respect to y, that's cosine y, all right? Then partial of n with respect x. Okay, careful here. The derivative of x cosine y with respect x, well, the derivative of x equals to 1 times the multiple constant cosine y, this is simply cosine y, all right? Minus the derivative of 2y with respect to x, well, y is held constant, so that's 0, okay? We don't need to write that 0. What do you think? Exact or not exact? It's an exact equation, right? Yeah, exact. So they match. So it's a match here. Therefore, the D is exact. So we're ready to evaluate a couple of partial integrals. Okay, let's use the right side of the paper here, the right side of the document. So that's the integral of m with respect to x, which is the integral of x plus sine y dx. Okay. All right, the integral of x with respect to x, that's x squared over 2, plus the integral of sine y with respect to x. What is that equal to? Any ideas here? Okay, negative cosine. However, we're integrating with respect to x. This is a y. This is just a constant. So that's just a constant sine times x. Actually, I don't like how this looks like because this is a little bit ambiguous because it's the x part of the angle. So I'm going to rewrite this as x squared over 2 plus x sine y plus c of y. All right? Just to avoid confusions with that x being part of the angle or something which is not. Careful. All right? All right. What about the integral of n dy? That's the integral of x cosine y minus 2y dy. All right? And what is that equal to? Okay, the integral of x cosine y. So here, this time, we are integrating the cosine function, which is positive sign. However, this x in front of the cosine, it's a multiple constant, right? With respect to y. So that's x sine y, okay? Minus the integral of 2y with respect to y, which is y squared, plus some other constant, but in this case, a constant with respect x, okay? All right. Actually, you guys might want to, or, I mean, I'd rather not, but you could omit the concept, but because in the end, they do not participate in the selection of the terms to create our solution, okay? But I'm just going to keep writing them just in case. Okay, so let's highlight every single term we have. Okay, so I see an x squared over 2. Do you see another x squared over 2? Looks like that's the only one. Okay, let me use a different color to highlight other terms. Okay, so, wait, what's going on here? There. Okay, well, actually, I should have highlighted it here. Okay, all right. It looks like I see an x sine y. Do you see another x sine y? Actually, it's in the second integration. Do you see another term other than x squared over 2 and x sine y? And if so, what do you see? The y squared, along with its sign, right? Negative y squared. Okay, so we're going to grab one sample of it. I mean, of the ones that repeat. Again, we just grab one. Okay, so wait, yes. So our f of x y equals to x sine y minus y squared plus x squared over 2. And let that be equal to c. You can do it like this or write another statement just having the function equals to c. It doesn't matter. All right? It doesn't matter. So that was another example of an exact equation. Okay, we have plenty of time for a couple more. Okay. All right. So let's see. On the next page, what do we have? There's okay, this is going to look like one of the homework, a few of the homework questions. So this time, we're given a differential equation. However, one of the functions is missing. So they're asking us to find the function m such that this is an exact equation. And of course, we're not going to do this by guessing. You don't want to do that by guessing. Okay, so what do we do here? Okay, so we're going to start by using the criteria for exactness of a differential equation. That is, using the fact that the partial of m with respect to y equals to the partial of n with respect to x. Okay? So, well, the partial of m with respect to y, actually, we don't know what's that function, right? So I'm just going to leave it as dm, as partial of m with respect to y. However, okay, dm, partial of m with respect to y equals partial of n with respect to x. But what is it that we differentiate with respect to x? This is going to be our n, x over y. And what is the partial derivative of x over y with respect to x? Well, so the derivative of x equals to 1, all right, times the multiple constant 1 over y. This is partial of m with respect to y equals to 1 over y. All right? What do we have here? Doesn't that look like a baby separable equation? except that we have the Jacobian symbol instead of the Leibniz notation. But I mean, it still works the same. So partial of m equals 1 over y, partial of y. Okay, how about we integrate both sides? So that's going to give us m equals to what's the integral of 1 over y? Isn't that ln of y, of absolute value of y, plus some constant of integration? So this is the function that has to be here in order for that equation to be an exact. And notice the wording of the question. It says, find all functions. Why is it all functions? Because of the plus c. Depending on the initial condition, we may get one or the other, one particular solution or another solution, all right? Okay, so very quick method to solve equations, right? I mean, unlike the Bernoullis or unlike the homogeneous, these are nice, right? Okay, the question here is, what if an equation fails the test for being exact? What do we do in that case? Well, we would need to find an integrating factor, all right? So remember what we did with linear first order differential equations? We multiplied the equation by some mu function and we compared it to the product rule, and then we did a little bit of magic here to turn it into a separable equation. Well, so we're going to come up with an integrating factor for the exact equation, all right? However, it's going to look somewhat similar, but a little bit crazier than the integrating factor for the linear first order equation. Okay, so what do we do? Okay, so number one, we know that m of x y dx equals to, plus n of x y dy equals to 0. Okay? So that, and let's suppose this equation, in general, failed to be an exact equation. What are we going to do again? I'm going to multiply by a function mu, but in this case, rather than having a function mu of x of y, mu of x, it's going to be a function of two variables, and that's because each coefficient of the x and the y are functions of two variables. So these integrating factors are going to be functions of the variables. Now, guys, well, here it should be understood that all these are functions of two variables. To abbreviate the notation, I'm just going to use the symbol. So I'm going to distribute, that's mu m dx plus mu n dy equal to 0, okay? So that's what we want here. All right. Okay, so here it is. For the d to be exact, that is, so it must be satisfied that, the partial with respect to y of mu m equals the partial with respect x of mu n. All right? What is that going to be? Okay, so let's evaluate this on each side. However, all these two factors inside of the parentheses are both functions of two variables again, just so we keep it in mind. So this means we need to evaluate this using the product rule. That is, mu with respect y times m plus m with respect y mu equals mu with respect x n plus n with respect x times mu. All right? However, we have a big problem here, okay? Well, number one, okay, let me solve for mu, okay? Let me have all terms containing the mu. Wait, what I mean to highlight this term, I'm going to move it to the right hand side, and that term, which one? This one right here. I'm going to move it to the left. Okay, I want to keep all the mu's without differentiating on the right hand side. So that is m with respect y mu minus n with respect x mu equals to mu with respect x, n minus mu with respect y, m. All right? But we have a big problem here because we want to solve for mu, right? That would involve solving a partial differential equation. And at this point, we're barely learning how to solve ordinary differential equations, not partial differential equations. Okay, let me write a note about this. Okay? So, this is hell since this is a PDE, a partial differential equation, right? However, we're going to look at a trick here, all right? So, here's a trick. Let me write it down. Trick. Let mu of x, y, so which is a function of two variables again, right? Let me keep reminding about this, okay? Be a function of just x. Of just x, all right? That'll simplify the problem because working with functions of one single variable turns everything into an ordinary differential equation, and actually that's going to be the case. All right? So, if we differentiate, so if we're working with a function of x, that means we will differentiate everything with respect x. Whatever has a derivative with respect y, what is that going to be? 0. All right? Okay? Because that's all terms of x, really. All right? So this means mu of y, now that it is a function of just x, differentiate something that depends only on x with respect to y. What's going to happen? 0, right? This will be equal to 0. Okay? So coming back to this crazy partial differential equation, m with respect to y, mu minus n with respect x, mu equals to m with respect x, n minus mu with respect to y, m. This is the guy that goes away to 0. Why are we solving a partial differential equation here? Because we have m with respect to y and m with respect to x. So having this just being a function of x simplifies the process. Well, the rest of the problem is going to be very straightforward. So that is mu. Okay, I'm actually going to reverse the order of the equation. Mu x, and I'm going to write it on the left, and all this, m with respect to y, mu, minus n with respect to x, mu. And I'm going to solve for mu of x, okay, by dividing both sides by n. All right? So, what's that going to be? This will be mu with respect to x, and I'm going to factor mu in the numerator of the right hand side. So m with respect to y minus n with respect to x, everything divided by n, okay? And well, this mu with respect to x, again, when you see this mu with respect to x, that makes you think of a partial derivative with respect to x because of the subscript notation. But remember, what did we say about this mu? Didn't we say it's only now a function of a single variable x? So I can write mu subscript x instead, okay, as d mu dx, okay? Well, This is equal to mu m sub y minus n sub x divided by n. And guess what? This is an ordinary differential equation. It's separable, by the way, right? I'm going to multiply both sides by dx, and I'm going to divide both sides by mu to obtain the following. Okay? So that's going to give me, okay, let me continue here. Okay? Mu of x, wait. No. d mu over mu equals to m sub y minus n sub x over n dx. How about we integrate both sides? All right? Okay, of course we don't know, symbolically, we don't know what m sub y and n sub x and over n is. Let's just leave it the way it is. Okay, so this is the integral of m with respect y minus n with respect x over n dx. And what's the integral of d mu over mu? Isn't that ln? ln of mu? I'm going to omit the absolute value bars for now. Okay, so to make this simpler. Okay, so how about we exponentiate both sides? So this will be mu equals to e to the integral of m with respect y minus n with respect x over n dx. And that's the end of the proof. That's the mu that will turn a non-exact differential equation into an exact equation, right? Well, that's actually the derivation, the proof of where it's coming from. Again, see how this puts together a lot, a separable equation, multivariable functions here and there, all right? Okay, let's flip the page. On the next page, you have the summary, okay? You have you have mu either as a function of x, all right, that's e to this monster integral, okay, or actually when we try to get this integrating factor, it may not work to get an equation that is not an equation, an integrating factor that depends only on x. So we need to check another alternative. Maybe it's a function of just y. Actually, you can derive this formula exactly the same way we did it here. However, by setting mu of x equals to 0, and that is considering a function of y. All right? Okay, how about we see an example of this? Okay, so solve its exact equation, xy dx plus 2x squared plus 3y minus 20 dy. All right, number one. Let's check whether partial of m with respect y, what is that? Okay, m with respect y, do you guys agree this is x? And partial of n with respect x, what is that equal to? 4x? Oh, shoot. This is not an exact equation, right? So, without what the formulas I showed you here, we are not going to be able to solve this equation, at least not the exact equations. And I don't think even with even the homogeneous equations wouldn't work, because we have a constant here, and here we have quadratics, and no, it wouldn't have worked. So we should use definitely this integrating factor. So number one, we're going to explore two options, okay? M with respect y minus n with respect x. So number one, let's see if the integrating factor is just a function of x. Let's see if it works. M with respect y minus n with respect x divided by n. All right. Okay, partial of m with actually we have it at the top, right? So x minus 4x, divide that by n, 2x squared minus or plus 3y squared minus 20. But actually we can see, okay, this is negative 3x over 2x squared plus 3y squared minus 20. This is not a function of just x. This is not a function of just x, unfortunately. Well, we have a second alternative. we have a second alternative here. Okay, how about number 2? Instead, let's compute n with respect x minus m with respect y. All right. Hopefully everything divided by m this time. Careful. All right. Okay, well, n with respect x and with respect y, they are both the same. So that's going to be this time 4x minus x, all right? Divided by the quantity, what is that? Xy, right? What is this? 4x minus x, is that 3x? Divided by xy, is that equal to 3 over y? Yes! Hell yes. This is just a function of just y, all right? If for whatever reason none of this works, well, then we need to find another way. I don't think this is separable either. No, this is going to be something else. But, well, at least this one is, can potentially be an exact equation. Okay, no. This is not the integrate. No. This is not m mu of y. This is just a yes function of yes, just y. Whoops. All right. All right. Let's find the integrating factor finally. So that is mu of y, which is equal to e to the integral of n with respect x minus m with respect y divided by m dy. Okay, this one we integrated with respect y. Unlike the other one, we would have integrated it with respect x. So careful. All right. So e to the integral. Okay, nx minus. Okay, that's actually the integral of 3 over y dy. That's e to the 3 ln of y. But again, basketball, the coefficient e to the ln of y cubed, which is y cubed. Now this is the integrating factor. That's the quantity we're going to multiply the original equation to turn it into an exact equation. All right? Yes. All right. Okay, so here we go. I'm going to rewrite the equation. xy dx plus 2x squared plus 3y squared minus 20 dy equals to 0. Let's multiply both sides of this equation by mu of y, which in this case is y cubed. Y cubed. What is this going to be? Okay, so xy times y cubed will become xy to the 4th dx plus y cubed times 2x squared is that 2x squared y to the 3rd power plus 3 times distribute 3y to the 5th and minus 20 y cubed dy equals to 0. Okay? So that is a whole new equation multiplied by some integrating factor that will make it an exact. However, we need to check the condition to verify to make sure. All right? So how about partial of m with respect y? Okay, what's a partial of m with respect y? Is that 4xy cubed? All right. What about partial of n with respect x? Okay, so with respect x, that is 4x y cubed. This is only a y that goes to 0. This is only a y that goes to 0. So, exact. Right? Exact. Okay. That means, what do we do? Evaluate the partial integrals. Right? So, let's evaluate. So, yes, exact. All right? Evaluate integral of m dx, which is, what is that? The integral of x y to the 4th dx equals to, okay, with respect x, That's the integral of x, which is 1/2 x squared times y to the fourth. That's because y to the fourth, it's a multiple constant, not an additive constant, okay? And I'm going to add some constant plus c of the other variable y. Okay, what else? So what about the integral of n dy? That is the integral of, oh, this madness here, 2xy cubed plus 3y cubed minus 20, I guess, no, yeah, minus 20, oh wait, y to the fifth, 3y to the fifth, 20y cubed, dy, okay? This is going to give us a bunch of terms. We're integrating with respect y. Okay, so the integral of y cubed, isn't that y to the 4 over 4? However, times the 2, it's going to turn this into a 1/2 x squared y to the 4th. The integral of 3y to the 5th power, that'll be y to the 6th over 6. But 3 divided by 6, isn't that another 1/2 y to the 6th? And finally, the integral of 20y to the 3rd power, that's going to be 20y to the 4 over 4. But 20 divided by 4, isn't that negative 5y to the 4th plus some constant of x. All right? Let's form our solution. Well, let's highlight every single different term. Okay, what about 1/2 x squared y to the 4? Do you see another one of those? Is there one in this? Yeah, there's one right here in the second integration, right? How about maybe, okay. What about 1/2 y to the 6? Do you see another one of those? I think that's the only one, right? What about, okay, let me use this one. What about the next? Okay, negative 5y to the 4th. Do you see another negative 5y to the 4th? That's the only one, right? How do we get the solution to the differential equation? F of x, y. Consolidate the results. That is, do not duplicate, okay? Get one of the green ones, only one, 1/2 x squared y to the 4th, and then plus 1/2 y to the 6th, minus 5y to the 4th, and let that be equal to c. All right? Final answer. All right? Final answer. All right.